Hey, I'm Max. Let's learn how to tackle this educator question, heights in a BST. So first, let's read the problem statement. We want to write a insert function that is given the root of a tree and an input key, and this will insert this key in the tree in the form of a tree node, and then update the height of every necessary node. It returns the root. You can see we're given some sample inputs, but I think these aren't super helpful to just look at their own. Let's whiteboard this out. So say I'm given a, how do I draw? Right here. All right, so say I'm given a node. We can say that this has value, I don't know, value 3. All right, scratch this. Value 3, like so. When we insert a node into this tree, the fundamental properties of a BST say that if the new value we're inserting, so say we're inserting a key of 1, since 1 is less than 3, we would insert it to the left. If we were inserting something instead, say 5, it would insert to the right. So how can we turn that logic into a function like this? Well, if you think about it, we first are given this root, and we're asked, we want to insert a number, let's think 4, into this tree, the tree containing this root. Well, what we can do is, if we are to kind of like solve this problem ourselves, we would look at the 3 and then say, okay, 4 is greater than 3, so I'm going to go to the right and instead insert the 4 at this 5 here. At that point, we would maybe move like so and insert it as the left child, since 4 is less than 5. But you can see that we're following a very similar line of logic for both the 3 and the 5. Essentially, the same problem, we're presenting ourselves with the same problem at the root of 3 and the 5 node. So that kind of gives us the intuition to solve this problem recursively. So effectively, we call insert first on this 3, and that in turn will call the insert at the 5. So, all right, we've established that we want to do this recursively. So the first thing when we're writing a recursive function is to establish the base case. In what case, when we call this insert function, in what case will we just return a value and not make another recursive call? Well, the simplest here is maybe just if the root is null, right? We can imagine that here at this 5 has no left and right subchild. So if we were to insert this 4, we know it has to go to the left subtree. But if we were to, recursively call insert on here, we'd be calling insert on a null pointer. So we know that if we ever get to the point where we're calling insert with a null pointer, we've reached the correct position in the tree, and we'll just return a new node with this value. So there's our base case, and we've already talked about our iterative cases, right? If we're at a node that's not null, and our key is less than that node, we'll just call iteratively on the left child. If we're at a key, or at a node where the key is greater than that node's value, we'll call iteratively on the right child. We won't worry about, the one case where the node and key could be equal. I think for this problem, we'll just assume that all of the insertions, all of the node values are distinct. All right, so we have our kind of recursive structure for how we want to get down here. At this point, this will return a node. So if we get to our base case with a null pointer, we'll return the new node. And then when we recur up, so we've just recurred from this stack call. What that'll do is that'll effectively continue execution in this stack frame here. And we've just received this node as a result of the call to insert that we made in this frame. So when we receive that, we can set this node's left child to the node, this node 4 that was returned by the insert call it made. Now at this point, we also have to update the heights. So this newly created node has a height of 1 because we know when we newly create a node, it's going to be at the very bottom of the tree. It's going to be a leaf. And this 5 previously had a height of 1 stored as well. But now that it has a new node below it, inserted below it, we need to update its height. So how do we do that? Well, we can't just take the height and increase it by 1. Because say we had a subtree here to 5's right with a height of, maybe like 3, right? Then 5's height would be 4. And even if we insert this 4 to 5's left, its height shouldn't change. So what we'll instead do, every value that has made a recursive call, every node that's made that recursive call, and is now receiving that new node, well, what's the definition of the height? We look at the height of the left and right subtrees, take the maximum, and then add 1. So here, when we look at the height of that new left subtree, it'll be that 1, but the height of the right subtree is still going to be that 3. So when we add 1 to the max of those two, we're still getting our correct 4. And again, we want to do this height update on every node along the recursive chain, because everything could have theoretically been impacted by this extra node that was updated, or that was inserted, right? If we didn't have this chain here, this 3 would have gone from a height of 2 to a height of 3. So I know that was a lot of talking, but hopefully that gave you an intuition on why you want to do this recursively and how exactly you want to update the heights and the nodes within each of the recursive calls. If you want to try and code it yourself, I recommend you pause the video here. Otherwise, I'm going to start coding the solution and you can follow along. All right, so before we worry about the heights, again, start with the actual insertion of the node. So again, we're doing this recursively, which means the first thing we want to handle is our base case, right? And we said that was if the root was equal to null pointer. This is a quick way we can write that. So if there's no root, we can't access, the left or right children of that node. We just know that that position, that pointer, is where we want to insert the new node. So what we'll do is just return a new tree node with the value key. And we can see here that when this is passed in, we'll get the constructor. And it actually, I made a small error here. It seems that the new node, we start with height 0 for the leaves instead of a height 1. But our code will sort that out. So okay, and then we want to now write a recursive call. So what if the tree node is not root? We need to navigate down to that correct null pointer where that key should be inserted. So the root here has a value, right? So if we look at the root's value and we notice that it is greater than our key, what does that mean? Well, that means that our key should be inserted to the left of that root node. So what we can do is we can call insert recursively on root's left subtree and also pass in that key. Now, if the root has no left child, right, what we're doing, what we'll see is that root left is a null pointer. And what that means is that on the next iteration, it will return the correct node. And we want to actually use this return value, right? When we've returned this tree node, say again on that call where there is no root left, we want to update the root's left node to be that newly inserted node. So what we do is we assign the root's left node to the call on insert on this root's left node. And that's essentially just to ensure that the new left subtree is updated as a result of that insertion. And alternatively, if the root's value is less than the key, we know we have to head to the right subtree. So we just have to do this the same recursive call, but instead calling with the right subtree. Again, this might fall through into the condition where key equals root val, but we're not going to worry about that for this problem. All right, so now if the root is null, it would have just returned a new tree node with a height of 0. Otherwise, it's just got either its left child or its right child updated. And as a result of that, its height might have also been updated. And we need to write code to reflect that new height. So if we update the height, well, what do we update it to? Well, again, it's going to be 1 plus the max of the height of the two children, right? And so we want the height of height of the right subtree and height of the left subtree, and we want to maximize between these two. So it may be tempting to just write here for the height of the left subtree, root left height. Done and dusted. However, you need to consider the possibility where root's left subtree is actually null, right? Root left is a null pointer. In that case, trying to access height like this will actually give you a segmentation point because you can't access that property when root left is null. So we need to account for that case. And what we can do is we can essentially say that if root left doesn't exist, if a node doesn't have a left subchild, we can just return it as having a height of 0. And a compact way to do this is using a ternary operator. So this will check if root left exists. Effectively, it will return true if root left is not a null pointer, and will return null or false if it is. And so if root left exists, then we can use this expression here, which gets the height of the left node. Otherwise, again, this colon stands in for an else with this ternary expression. It will just return 0. So effectively, a non-existing node is just counted as having 0 height. And that ensures that if there is no left subtree, it will instead, max will instead just take the height of this right subtree. And we always know there's going to be at least one subtree because we've just inserted into one of them. Again, do the same thing here with the right subtree. And again, we'll maximize the 2, add 1 to get the root's new height. And then, put a semicolon, we'll return this root. And then again, we'll ensure that these recursive calls can properly update their subtrees with the updated nodes after insertion. So say, remember in that diagram, say I've just updated this 5, and I've updated its height. I can then return it, and then in the where the 3 made this recursive call, we can update its right node to be this 5. So let's run our code, see if we can notice any errors. It looks like I've forgotten a semicolon. It happens. Try it again. Compilation successful. Let's submit. And we've passed all our test cases. So there you go. That is how we can write, I guess it doesn't let me show the whole thing, but how we can write our insertions and height updates in a BST. In the AVL project, it won't be quite as simple. You're actually going to be working with a balance factor. Actually, no, I think you store the heights in the tree, not the balance factor. So you will be doing this exact line of logic, but you will also need to account for the rotations, which we'll talk about in a later video. So hopefully that made sense. If not, you can always just ask a TA. And good luck on any future problem you do and on Project 1.